So welcome back for our second discussion of the day today, after the very fruitful discussion that we had previously. And now we're going to have Mauricio Martinez from North Carolina State University talking about non-Newtonian fluids, Jesus, I can't speak, fluid behavior in hydrodynamization and lessons from transasymptotics. Thank you.
Thanks, Ines, for the introduction and the invitation to this event. I am very glad to be here. First time that I'm into such a broad audience. And what I will discuss today is mostly some issues that arise in the description and some interpretations about what transasymptotic and resurgence does when you apply to hydrodynamics. So yesterday we had a very nice talk from Michael Heller. I'm not going to repeat some of the steps that he did, but instead I'm going to focus on some aspects of kinetic theory that sometimes are more known for specialists who dedicate their lives to this. And since the idea is to sparkle discussions, then it might help to everybody. So just to remind you, we have an initial state, which is a non-equilibrium system with many degrees of freedom. And this system has some particularity that as time goes to infinity, then you have like a fluid. And the question is how this happens. And the first part that one has to understand is that this stage of non-equilibrium is characterized by relaxation scale, where all the modes are more or less equally excited. But if you wait as a function of time for time larger than this particular relaxation scale, which can be on the order of the mean-free path, or for large systems, because we are considering only macroscopic dynamics, then you just have that only few degrees of freedom survive. Survive the entire evolution, and those are the dominants in the long time. And this is the way that we understand how, at least in a cartoon picture, how this hydrodynamization process happens, right? And in recent years, we start to see something that emerges from this picture, which is that there are certain universality properties related with attractors and what happens in some asymptotic regime of the particular dynamics that you have. And what I'm going to try to address is like, what are the lessons that we have learned about transasymptotics and this overlap between trans-series and dynamical systems, and what we can learn a little bit about dynamical systems and up to some extent. So that's what more or less I'm going to talk about, and I'm going to focus on what happens in kinetic theory, particular Boltzmann equation, which is a particular setup that will allow us to do accurate calculations at numerical and analytical level under control. And then the agenda that I'm going to provocate the discussion is like there are some ideas that emerge from this analysis of transasymptotics and what happens in some particular regime. The first one, which I'm going to go with certain detail, is the interpretation of this trans-series in this concept, which basically have a constitutive relation, which is the one in the upper side. When I have, for instance, the shear viscous tensor that is expanded in terms of gradients. But then what I'm going to try to say is like, for certain situations that have been studied analytically, we have observed that, or at least the studies that I have made so far is that one can show that there is a particular resummation which makes the transport coefficient depending on the flow velocity. The question is how this emerges and how this trans-series tell us about. And the second one, which is a little bit more subtle, which is in general, we always focus on kinetic theory. We have a lot of degrees of freedom, and then they decay as a function of time. But at the end of the day, you just have a very few of them. And this tells us that it's also the emergence of an attractor, even at the level of the distribution function. So just in some minutes, I'm going to say what the distribution function is. And the question is, how to characterize this and how to study those situations and how can we learn from that and what transasymptotics can tell us about it. Okay, so so then of course I have not done this alone, and the progress that I have made is thanks to the collaboration with a great group of people. Alireza Betash, who is now was graduate student at NC State and now is working in his own startup in machine learning. Carlos Nicolás Cruz Camacho, who is a student at grad student at Illinois, and my former master student, Sho Kamata, who was a postdoctoral researcher here and now is in Poland, Hao Cheng-Shi, who is in NC State University as a grad student, and two professors at NC State University, Thomas Schaeffer and Vladi Eskokov. And the references that I'm going to more or less talk about are just landing at the bottom of the slide. And okay, so just Boltzmann equation. Boltzmann equation is nothing else than an evolution equation for the distribution function. And the evolution in time and space is telling us how and this equation describes the evolution of the statistical properties of a system, which is described by one distribution function that lives in 7 dimensions, has in the sense that it depends on time, position, and momentum. And the equation is very simple in principle. Looks simple, but it's not, because it has very nonlinear couplings between different components, and therefore is very highly non-trivial to find exact solutions. But there are 3 parts. The first one is there is a diffusion term that tells you how particles expand freely without any interactions. The second one is that if you have some force, like electromagnetic force, gravitational force, or any mean field force, then you have some term there that is proportional to the gradients of the momentum of the distribution function. You have also the particle imbalance. And the particle imbalance is nothing else that if you have collisions among before and after, it tells you what is the gain and the loss of those collisions and how this affects the probability before and after that event happens. And of course, in the discussions that I'm going to address today, I'm going to briefly reduce my discussion because the collisional kernel can be as complicated as you want, depending on the particular interactions. And one of them was recently performed by us, which is the so-called diffusive approximation that leads to the Fokker-Planck equation. And the other one was something that Michael Heller talked yesterday, which is the relaxation time approximation, where you consider only deviations of equilibrium that happens at a certain relaxation scale that is a function of the temperature. In the diffusive equation, just to be more precise, you just expand around the collisional, the scattering amplitude or the amplitude square in terms of perturbative diagrams, and then you just choose the ones that are important in the small angle. In this case, are just nothing else than 2T channel diagrams, and which are in the figure. And okay, so this is one of the first approximations. The second approximation that I'm going to use is a toy model, which is Bjorken, where a system expands longitudinally, and the volume of the of this particular cylinder, it just grows as a function of time. And this proper time is nothing else than one of the parabolas that you see here in this corner. And the description was like if you have a fluid that moves in longitudinally in time and in the longitudinal direction, then all the dynamics is really encoded in just one of those constant hyperbolas. And Michal yesterday talked about that, so let me just skip quickly. And under those two approximations, you can show that the equation of motion for the Boltzmann equation gets completely reduced to this particular relatively simple equation, which still is an integral differential equation because the collisional kernel has some terms that are integrated over the momentum of the particles. The important aspect is that this particular setup, which is in the Bjorken case, gets reduced to just 3 variables. Before we had 7, now it's 3. So it's a little bit easier to handle it, but it still is not so, still is highly non-trivial. All right, so, and here is the part that I start to like kind of deviate from what was discussed yesterday. because solving the Boltzmann equation in general, even in this setup, is very highly non-trivial. And in general, Grad proposed a method to solve the Boltzmann equation. And by the way, this method has been used in other type of fields, like for instance, in the Schwinger-Kaldish techniques. They expand in some sort of orthogonal polynomials. And in this case are polynomials that are in energy. And you have some tensors that are irreducible tensors in the momentum, and some moments which are irreducible under the Lorentz little group of Lorentz. And there is the expansion is always carried out in general around background distribution, which is usually taken as the equilibrium state. That's not necessarily the case, but that's the idea. And of course, physical observables, what are physical observables in kinetic theory, are nothing else than average. For instance, the energy momentum tensor is weighted by the probability distribution times the product of two momentums of the particles. And then you average over all those all the phase space available for the particles, and you end up getting your energy momentum tensor of the system. And in general, for instance, for a fluid, we have that there are two pieces. One that is the equilibrium piece, which is the energy density plus pressure, which is the enthalpy, nothing else. And in this case, you have also another vector, which is it's going to be identified as the fluid velocity. And let me tell you that I'm going to work in the Landau frame. And you have also other method, other variable, which is the shear viscous tensor that can be identified with one of those moments, which in this case is rho nu mu 0. So some comments before continuing, because I'm speeding up maybe a little bit too much. And is that in general, and this is one of the questions that I would like to ask to the experts in trans series who have done in other subjects, have worked on other subject, which is like, there are also some orthogonal polynomials expansions. And one of the aspects that enter into that particular expansion is the analysis of how you get to some particular state in the long time, or in the particular parameter that you have defined as time or something like that. And in particular, the question is that I always have is when you do these expansions is how to determine the degrees of freedom. That is one of the questions that I'm going to ask later on. And another question that I have is like, how well defined are in general those type of expansions? For instance, in kinetic theory, we know that there are certain conditions for the distribution function to be expanded like that. But I just don't know if there are some particular aspect that enter when people do these expansions in orthogonal polynomials. And as I said, I've seen people applying it in Schwinger-Kaldish, solving Schwinger-Kaldish equations. So it would be nice to hear something about that. I don't know if somebody has some idea at this point, or if we leave it towards the end. Okay, so there is an issue with this particular expansion, that you don't have an expansion parameter, which is a disadvantage. However, the evolution equations of dissipative quantities can be obtained exactly by taking derivative over their own definition. But when you do that, then you have another problem that enters into consideration, which is that you have a tower of equations among different among tensors of different orders, and therefore the equations become more and more complicated. So let's say, for instance, tensor of rank 2 gets coupled with tensor of rank 3 and rank 4. Tensor of rank 3 gets coupled with tensor of order 4 and 5, and so on. So in general, then how do you solve this? And then you need a systematic power counting, and that was developed in 2010, not so long time ago, by different authors, Denicol, Gabriel Denicol, Harry Nieme, Ethel Mornar, and Dirk Richke. That's why we use DNMR these days, which is a systematic power counting in Knudsen and inverse Reynolds numbers at the level of the equations of motion. And there is a very highly non-trivial aspect, which I really took me a while to understand, which is that each of those modes have a characteristic time scale, which ended up being an eigenvalue of the linearized collisional kernel in a particular eigenbasis. And the paper is about all those technical details, but in principle is that a little perturbation decays near to the equilibrium with some particular relaxation scale. And implicitly, you have the idea that there are different modes, so different modes scale differently. Or they have a particular relaxation scale, and there is a hierarchy of scales. And you choose the slowest one. So in other words, whatever equations of motion that you ended up deriving, you will be able to truncate, provided that assumption. And what I found it wonderful about that work, which is absolutely beautiful, is the fact that it allows you to do the truncations systematically and with higher order of accuracy. And when you compare with solutions of the Boltzmann equation, it's in some situations it works very well. So I am not going to talk about comparisons of exact solutions and so on, but in certain situations it shows a very higher order of accuracy. And it has been used as one of the models to describe the physics of the quark-gluon plasma. So it's a very beautiful work, really. And well, this is like kind of the general aspect. So I'm going to start more about what we do. We proceed with this philosophy, and we expand around some particular set of orthogonal polynomials which respect all the properties of the Bjorken flow. In this case, we are going to expand around equilibrium, and we are going to characterize the expansion with some orthogonal polynomials, which are those P2L, the Legendre polynomial, sorry, in some angle, which is the azimuthal, the angle that of the anisotropy, because the system is expanding longitudinally, and some moments, which are these CLs. Okay. And the advantage is that for both, for the Bjorken, for the Fokker-Planck, and for the relaxation time, the eigenbasis diagonalize the linearized collisional kernel. It allows a systematic perturbation theory. And the other important aspect is that the problem of solving a nonlinear integral differential equation is mapping into solving a set of nonlinear ODEs for the moments. And this is one of the properties, or one of the cool things about using moments method, which is that you can map information of extremely complicated integral differential equations into solving a set of nonlinear coupled differential equations. The other cool thing that I like of the method is that any observable that depends as a function of time is nothing else than combinations of the equilibrium piece, which comes from the expansion, and some other combinations of those moments weighted by some coefficient that is nothing else than the azimuthal integral of the Legendre moments, or projections over that. And that's very nice, because, for instance, if you write the energy momentum tensor for the Bjorken case, as Michal explained yesterday, you have a diagonal component where the diagonal terms are again the energy density, the transverse pressures, and the longitudinal pressure, which can be re-expressed, as I said before, into those moments. And in principle, at this point, you need only one of those moments, C01. And this C01 has a physical interpretation, which is related with the pressure anisotropy. So in other words, the dynamics is going to give even in terms of the energy density, which is proportional to the temperature, and the pressure anisotropy. So that's really cool, because all this complicated dynamics boils down to just two variables for the particular Bjorken case. Now, the other aspect is that, let me just focus what happens when I just truncate this, and the equations of motion are nonlinear when you calculate it exactly. And there is a trick that was invented by Michal Heller and his collaborators, which was that I can just map all that information in terms of this W variable, which is nothing else than something proportional to the inverse Knudsen number. And when you do that, then you find a differential equation, which is nonlinear for only one mode, for the type of C01. And the interesting aspect of that equation is that equation depends explicitly in the variable W in the right-hand side. So here is the part where dynamical systems starts to play a role, because those differential equations are called non-autonomous because the explicit dependence on the W variable. And depending on the regime where you are focusing on, you can have different asymptotic solutions. In particular, what I'm going to call when the W variable is large, which in this case means a small Knudsen number, so near to equilibrium. I'm going to call that the IR. And near equilibrium, most of the physics that we know comes from linear response theory. But there is another regime where the W is very small, which is a region where the Knudsen number is very large. And therefore, we have something that is extremely far from equilibrium. Okay? So when you solve this equation, you start to find out something really, really nice. So pick up your initial condition that you want. And then you have the pressure anisotropy as a function of W. There are the terms in blue are the nonlinear effects, which play a role mostly at early times. At very late times, the first term that is proportional to C01, then is the one that dominant. And there is a little subdominant effect, which enters in a region that is not so far from the asymptotic value of the solution. And of course, this is just a pictorial cartoon picture. But what happens when you are very, very close to your asymptotic value when W is infinity? Then you have some, you can show that the system admits some asymptotic solutions. And those asymptotic solutions are nothing else than what you know in linear response theory, as I say. So everything is linear, so you can really show that the coefficient that matches the Knudsen number or the W variable is a transport coefficient. And therefore, the physics of the IR is related with the values of those transport coefficients in this particular scenario when you use the differential equation to find those numbers. But if you really start to consider what happens with those coefficients, you start to see that they grow factorially. And this is an indication that your series is ill-defined, or in other words, the radius of convergence is 0. And there are different ways to circumvent. Michal yesterday talked about one of them, which is using the Borel transformation and doing an analysis of the Borel plane. The method that I am going to address, and that is also something that will be interesting to discuss, is slightly different. But before to go to that, let me just show you what happens when you just compare this exact solution with the asymptotic expansion. And I'm going to just put the first and second order, which are the red and blue lines. And the first thing is that you start to see that at late times, no matter what initial conditions you have, and you can do that for difference, the perturbative expansion kind of works, and actually it works much, much better than what you think, because you think that the radius of convergence is completely 0, and therefore it should fail dramatically. But you see that there is certain agreement, but it starts to deviate for when the Knudsen number becomes large, or when the W variable becomes small. And in that particular case, the anisotropy, the expansion, the asymptotic expansion matches relatively well the exact solution when the Knudsen number is not so small, which is in the order 1. And this is one of the indications that we have that the pressure, that you don't need to be close to equilibrium to apply linear response theory. You can even go beyond the regimes where the Knudsen number can be large. The other aspect that you see is that clearly there is a deviation for some initial condition, and therefore it tells you like, these asymptotic solutions are not enough to describe the system into its full glory. And here is where resurgence start to help you, because the basic idea then is to reconstruct a solution of the differential equation by analyzing the asymptotic behavior in some regime. And one of the physicists that I really admire the most is Peter Arnold, and he always told me when in some school that I attended years ago that when you know a limit, of a particular theory, then you can learn a lot. And that is precisely what we did by learning a lot from this divergent series. Because you can know, by knowing the asymptotic behavior of something, you might be able to reconstruct in some cases the full function, provided the information about what happens around this particular asymptotic solution. And this is what you do. And this technique, originally, to the best of my knowledge, was developed entirely by Ovidio Costin. It was introduced in relativistic hydro by Gokshe Basar and Gerald Dunn. And we work on those ideas and generalize further for different type of systems in kinetic theory. And the basic idea is, again, I have a differential equation, but I can perturbate around the equilibrium and just keep the linear order term. And what you ended up finding out is that just by analyzing this at a given order of the expansion, you find that the perturbation decays exponentially with some power law. The exponential term has a dependence that is related with the Lyapunov exponent. And the Lyapunov exponent, depending on the stability of the system, it can be positive or negative. In this case, ended up being positive. And therefore, it means that it's stable. And then you have also some correction, which is the correction that I say, that is like you are a little bit further from the where the asymptotic solutions works, and that is a power law behavior that enters there, which we call it anomalous dimension in analogy with what happens in field theory. So you can show that just by knowing the fluctuations, you can continue doing this recursively to each order of the gradient and to each order of and for a given order of the gradient also, you can continue expanding around that. And as a result of that resummation, you ended up finding out that this asymptotic solution that was fully divergent can be written now as a complete series in itself. So initially you have the expansion in the asymptotic expansion, but now when you start to add all those fluctuations around the particular fixed points, asymptotically, you resum a bunch of exponentials and a bunch of power law terms, which are a series on itself. And just for illustration, I compare what happens when I just calculate a few of those terms, and I just start to add them and then start to compare with the exact solution. And I start to see that actually I can get a very, very accurate result. Of course, there might be deviations. In this case, I truncate them. And those truncations also imply that those series will have, if I truncate that, those series will have some finite radius of convergence once I truncate. So what I mean is, like, I am not summing here until infinity, but I'm just truncated arbitrarily just to see how it goes. Somebody was asking something? Okay, so I continue. And this is, again, a very impressive success. And this is more or less what not only me, but different people have done so far. But the interesting aspect of this is that there is also some sort of analogy with what happens in quantum field theory, because those fluctuations, remember that the W variable
One
is,
thing,
yeah.
There's a question. If you have a question, please just unmute yourself and ask. Not a problem.
Okay, hi.
Hi.
I wanted to ask, how do you find the IR fixed point here?
Oh, that's a good question. Thanks for asking. So when you have dynamical systems that are non-autonomous, like this one, the fixed points are not the zeros of the right-hand side of this equation in general. They emerge as limits. And what we took was the limit when the W variable goes to infinity. And you have to analyze, you can have either one or many of those terms. From there, you start to classify which are stable, which are unstable in the usual standard way. So in this case, we knew that basically because at least we knew that the asymptotic solution was going to zero, and that was the hint that we had for when W goes to infinity. So that was the hint to know that the asymptotic fixed point was zero. But in general, if you have something much more complicated, which it can happen, you have to have some guidance from the asymptotic solution always to know more or less how what fixed points you are dealing with. But they are limits. So this is something that is different, and I insist on that. So usually you fit the derivative equal to 0, and that's the way that you extract fixed points. Here are limits. So in simple words, I knew the behavior of the asymptotic solution, and that was a good hint about why it was going to 0.
Thank you.
All right, so here is the part that was our interpretation, and it's also something that will be interesting to discuss, which is that if you are able to have the solutions in terms of this series, I can really rearrange all the solution in 2 pieces. One, which is the typical gradient size. So you will remember that when you do any particular perturbative expansion, you have something that is proportional to the coupling constant. So the coupling constant in this case is analogous to the gradient size, sorry, is analogous to your coupling constant. But then you have assummations over all those fluctuations around my particular fixed points in the IR limit. And this resummation is a function in itself, which encode, as I said, the summation over all those transients, which are those exponential terms multiplied by this power law behavior of the solution. And there are 2 properties that I really would like to address for the following, which is one, that in the limit when W goes to infinity, the only term that you have is the IR perturbative coefficient, which you can extract directly from the differential equation, but also that in the linear response theory, the perturbative expansion is proportional to transport coefficients. And if I just match what this limit of these functions are with the particular and associated transport coefficients given by my linear response theory, for instance, I can do that for the shear viscosity, then I have immediately a relation between the particular function associated to, or at a given a particular function that depends on the order of the perturbation, and that function just in the limit when W goes to 0, of course, the exponentials go to 0, and therefore I can just match with the transport coefficient. But this is intriguing because nothing forbids me, and if I start to expand this term, nothing forbids me really to associate a particular transport property at a given as a function of my Knudsen number with some non-equilibrium transport coefficient. What I mean is the following, that I can just basically promote the idea that the transport coefficient can depend on the gradient size. And when it depends on the gradient size, it's going to be related with the summations over all those transients that emerge in my transeries. By doing this, then I can write the usual linear response theory, where I have again the typical gradient size, which is the W to the minus something, and then the associated coefficient that is there is nothing else, which is it's not a coefficient anymore, it's a function. And this allows me to just generalize the idea of transport coefficient to non-equilibrium regimes. And what is the physics? And this is the physics that, and that is one of the hints and one of the most beautiful things that I saw when we were doing this work, because we could relate physics of what does it mean that it depends on the Knudsen number. And what it means is that there is a connection between this, between the physics of the resummation and non-Newtonian fluids and rheology of fluids in general, which is like in this cartoon picture, like you have that the shear viscous tensor is proportional, for instance, in this case of the 2 parallel plates, it's proportional to some gradient of the fluid velocity. And the response of the system against the force is nothing else weighted by some eta that is microscopic. But if that happens when I am pushing a little bit slow the plate at the bottom, at the top, sorry. But if I push very hard, then it happens that even before the system relaxes to equilibrium, the fluid can be have different modes excited, and all those modes can be just encoded into the transport coefficient. So in other words, my transport coefficient starts to depend on the typical sizes of the gradient. And this physics is what we see, for instance, in ketchup. You know, when you are a kid, you just push the ketchup bottle, and if you don't push it a lot, then it will not flow. And depending on whether or not, and there are different type of fluids of this type, and depending on whether or not you increase the shear rate, where you can have like the fluid becomes harder against the movement, and that is the shear thickening, or the fluid becomes like it flows actually even faster, like what happens in ketchup, and that is shear thinning. So that is the type of physics that you want to look at it. And that is the type of physics that you ended up finding when you start to resume those gradients. And therefore, what this Transeries is doing for you for free is resume non-perturbative contributions when the dissipative corrections are large. When you perform the resumation, then transport coefficients are renormalized. And in other words, the interpretation that I have about this idea, which comes from resurgence and transasymptotics, and by the way, this idea of, I should have said that this is called transasymptotic matching. As a result of that, then I can say that each transport coefficient gets renormalized after I perform this resumation of over all those transits or all those modes that are in non-equilibrium. And once I do that, then my fluid, the description of my fluid, presents non-Newtonian behavior. What is also very cool is that because of the limit of those functions at infinity, implies automatically that you will have an evolution where when the system is far from equilibrium, then the transport coefficient gets effectively reduced. And that was something that was pointed out many years, 10 years ago by Edward Churiak and Michal Lubliński, that they proposed this idea, and Jean-Paul Blasot also did some, and Lijan, they did some work about that. And it was related with the fact that if you are in a non-equilibrium situation, then the transport coefficient can be substantially reduced, and therefore it can flow faster. And it's intriguing that that might be the case for the quadron plasma. Of course, we need experimental data to verify that idea, but the thought is very provocative. And what we ended up also finding out is that depending on the initial condition, you will have a different history deformation of your fluid, and therefore its rheology. And in all the cases, you get that at late times, the transport coefficient matches the asymptotic value given by linear response theory. But in the middle, there is a very neat transition where, which is transient in the sense that just for a short period of time, the system starts to like kind of move away from its initial value, so its initial gradient, towards the asymptotic value. And this particular aspect, how this transition happens, can be described by an evolution equation, which is interpreted in our case as a renormalization group equation for the transport coefficient. And the reason is because the W variable, as I said before, is related with the Knudsen number, which characterize sizes of gradients. So in other words, when you have quantum field theory, you have also some energy scale that can tell you like where you start to evolve. In this case, it's analogous to my initial gradient size. And then afterwards, I know how the transport, in this case, the observable in quantum field theory evolves as a function of that particular variable. In this case, my variable is precisely the gradients and the size of the gradient. And this type of equation can be derived explicitly. We did it in our work completely. So far, we are the only ones. And it can tell you how the transport coefficient evolves as a function of time. So I am also providing, together with my collaborators, an interpretation to those functions, which are really basically the resumation of those functions in code, also the deformation history, which is given by some energy flow equation. So in other words, you can use those resumations in a very neat way, like what we do in quantum field theory for these cases. There is, however, a very particular aspect that this is not like in quantum field theory, because you have the explicit dependent on the W variable in the right-hand side. And that is related with the fact that the dynamical system is non-autonomous. Okay, so questions so far to this comment?
So I have a question, Maurizio. So I'm not sure if I understand correctly, right? But like when you have a transseries, you have like the, like this 1 over W power law part, like 1 over W squared, etc. And there are exponences, right? So what you're proposing is to take like these exponential terms at each power of like 1 over W and just resum them, right? And define new 1 over W series in which the parameters at each 1 over W term, 1 over W squared, and so on and so forth are functions of W. And my question is like, what are the convergence properties of this new series?
If you sum to infinity,
yeah, of the exponences, yeah.
Yes, if you sum to infinity, those functions are Borel summable as far as we were able to.
Sorry, can I just interject? They're convergent, not Borel summable. They're convergent.
Yes, sorry, they are convergent. Sorry, thank you. Yes.
That series converges.
Okay. So that was my question. Yeah. Thanks.
Yeah, thank you. Yeah.
Can I just mention another comment, Michał? So you are actually not summing all the exponentials associated to W. If you can see the zeta, is it zeta or a
zeta 1, all the transmonomials, yes.
So, but it has an exponential of the W, so you're actually summing different powers of W associated to the exponential. So it's kind of a mix. It's not just keeping W to the -1 and summing all the exponentials. It's not exactly like that. Sorry, just a small comment.
Yeah.
Well, I came in late, so I'm asking a very stupid question. So the fluid mechanics people would derive non-Newtonian constitutive laws by looking at molecular interactions and things. So does that have any relationship to what you're talking about?
Yes, I am trying to, what we find is constitutive relations for non-equilibrium systems in this particular setup.
Why would it need to be non-equilibrium?
In this case, it's in non-equilibrium because that's the physics of the problem. The problem is that this W includes large corrections to the pressure anisotropies, for instance, which is one indicative of that. And the deviations for equilibrium are extremely large. That's why, for me, it's an indication that I'm far from equilibrium. I don't know how to, I have not seen, I just saw one work, I remember reading one article about that, where this is derived in some models that I was really not able to understand completely the physics of the model, but the idea is also to try to get something similar there, but they are not necessarily close to equilibrium. Sorry, far from equilibrium. It can be also there, but I don't know how to do this technique there.
Yes, I mean, it would just much more generally, it'd be very interesting to compare these approaches to what you'd see in general non-Newtonian fluid mechanics.
Because, I agree.
Because I'm not sure that community would recognize any of these arguments, right?
Yes. I agree with you. And if you have some reference that are available, I will appreciate, because we talked about it, but we didn't go so far. But in this case, the interesting aspect to our work was to generate constitutive relations, which in general are thought to be close to equilibrium, but in this case for extremely non-equilibrium situations. And the interpretation is I think that is kind of neat.
Yeah, it'd be good to talk some more. Thank you.
Thank you. Okay, so
sorry, just before you continue, Victor. Yeah, sorry.
Hi, sorry. I also have a question, maybe on the same lines as John's question. So I'm confused about the interpretation of this dependence of eta over S on W. So I understand that you view this ratio, eta over S, in light of the validity of the asymptotic solution in 1 over W. So you interpret this coefficient in front of 1 over W as eta over S and link it with the transport coefficient. But my question is, what can you do with this dependence that you find here at the level of the hydrodynamic equations. So a hydrodynamic physicist would write down the hydrodynamic equations, then write down the constitutive relation for the non-equilibrium terms, and then solve it. So if I use this dependence of eta over s over w in the equation for hydrodynamics, what happens?
I don't have an answer, being honest. I have been thinking about how to do this in general, and I have not found a way to solve it. So far, there are very few words about this non-Newtonian aspect of non-equilibrium physics. And I think that we should just continue working on that direction if this idea really can be systematically applied for more, for instance, in more realistic geometries. I don't have idea about how to do that. What I find it pretty and very provocative, more than pretty, is that it's very provocative that you start to show that the ideas that come from trans-series and resurgence can automatically be understood if you reinterpret what the gradient expansion is when you perform those resumations. But I just don't know yet the answer. I don't have the answer, sadly. But it's a very interesting idea to explore. There are some resumations, just to add to your comment, that some authors in non-relativistic fluids have, as somebody else mentioned previously, that they have been doing some particular resumations, even near to equilibrium, where it's known that some fluids present non-Newtonian, non-Newtonian behavior. And but I really was not able to understand exactly the approximations. It's not my area of research, and I am just actually learning to see if this can be done systematically for relativistic fluids. Sorry, I cannot give you a full answer to your question. It's something that I also have thought, and it's an interesting point.
But this approach is derived in RTA or hydro?
We did it in RTA, and we did it in the Fokker-Planck equation.
So what about if you try directly the relativistic hydrodynamic equations?
I don't know.
So summing the terms that Michal presented yesterday.
But what Michal presented yesterday, it's similar to this up to some extent. I am just doing some other technique and some other interpretation. That's fine.
Okay, thanks.
Yeah, thank you.
Mauricio, I have a question.
Yes, please.
From what I remember from the time series applied to holography, then usually those exponential terms were associated with some non-hydro quasi-normal modes. So they were also associated with some free coefficients, which came from initial conditions. So does this problem appear here, or it's somehow not appearing at all?
It's in this sigma. And that is it's a very highly non-trivial question. Thanks for asking that, because it's very interesting. The way that we never went to water plane. So let me just be clear about that. We never really did it, and there are issues that I really have been puzzled about that approach, but that's okay. It's my lack of understanding probably, but that sigma is when you solve systematically the perturbation around the fixed point for a given order of the gradient, that sigma appears as an initial condition of the fluctuation. But that initial condition is, keep in mind that is a solution around that is a solution of the fluctuation near to your IR fixed point. Now, when you solve numerically, you never give the initial condition in the IR. You give it at very early times, or what I call UV, and in that case, the difficulty to determine the sigma is translated into how to connect the IR data that you have from your perturbative series with your UV data. I have not been able to find an exact method to do that. We discussed with different persons who have worked on that, and the way that we did it at the end was like, since we were doing systematic truncations, for instance, to generate this plot, we did the Pursman's approach, which was like, okay, we have a polynomial, we put the W as small as possible, And then we put the initial condition in the left-hand side, and then we determine the sigma. Because we truncate, we never sum until infinity. Numerically, you don't. And there is certain uncertainty that you have associated with that, and that uncertainty precisely because you don't know how to connect entirely the UV data with the IR data. At least not, we didn't find a way within this approach. So it's related with what you say. So thank you for asking that question.
Can I ask a question now?
Yeah.
So Mauricio, so in Bjorken, every gradient goes like 1 over tau.
I mean, W variable.
Yes, 1 over tau, or you can write everything in terms of W, right? So the point is, how do you know that in the thing that you're calling 8 over S as a function of W, that you don't have contributions that are not necessarily related to really shear viscosity behavior? Because all of them are, all of them are the same thing, right? So you cannot tell.
You have a lot of contributions, but you don't see that here clearly. You see that when you that's why I wrote here the renormalization group. You sum over all the sectors in the perturbative expansion. So you are coupling, all of them are coupled. So it's not only depending on one, the renormalization group equation combines with everybody, and that is expected.
Yeah, but I mean, if you just think about this tensorially, right? So sigma mu goes like 1 over tau in Bjorken. But any other combination that you can do with sigma or any other gradient that has nothing to do with the same symmetry of shear will also go with 1 over tau to a power. And here it is all summed together into the same contribution to 8 over S. So I'm not saying that it's not correct. What I'm saying is that I don't see how to, in Bjorken, I don't see how to clearly distinguish contributions from different tensors.
We did it. That's a good point. So we did it because you can really show how the shear viscosity, when you do that, when you start to include, here I am just taking, remember that this is a toy model when I truncate. So that's why I can do almost everything with relatively facility. The moment that you start to add more moments, tensorial moments and etc., everybody starts to get coupled with everybody. So the transasymptotic condition, at least for this dynamical system, works, but the energy flow equation becomes more complicated, and you have a highly non-trivial dependence on different sectors, not only perturbative and non-perturbative sectors, tensorial and non-tensorial ones. We did it more in the paper of the Fokker-Planck. This paper was more with one mode and so on, and you see that. And in practice, I find it we were unable to really solve that problem in general analytically. In the relaxation time, you can do that locally, and it's exact. It's very cute result. But if you try to do that beyond, it's impossible. It's more like you have a highly non-trivial system of differential equations that you are able to resum at a given order sector, which is allowed that in this case. And from there, you just try to obtain what you do if you do some certain approximation. But I agree with you that there might be other contributions there, but those contributions are also hard to evaluate. So yeah. This is more, this equation at the end of the day is more like to provide an interpretation, a physical one, which I think that is correct for this particular toy model. If you ask me, going beyond, yes, you can derive some similar equation, but it's unsolvable.
Yeah, my point is more like if you try to do this not in Bjorken flow, but in
general, you will have the same. That's an unsolved problem. I would like really to see if one can really do something in some model that is tractable, at least within some approximations, and see what happens. I have been digging in this non-Newtonian fluid literature, but I have not found really much. And one of the problems there is always try to derive constitutive relations for non-Newtonian fluids. It's not really an easy problem, even in non-relativistic fluids.
Yeah, so just one comment before I go. So it's just that normally what you do, you define new variables, right? If you want to solve this as a new hydro, this 8 over S becomes a new field that has to evolve. That's what you would do. This is, I guess, is probably related to the point that Mike will make. Okay, thank you.
Yeah, I guess since we're already in questioning mode, I'll just join. Actually, related to what Victor was asking earlier. So it was my understanding, right? So if you do this resummation, you get your W-dependent E over S. If you were then take this E over S and plug it in, say, a second order and gradient truncated DNMR equation, would it then agree better with the exact solution in the model? To use this effective E over S?
I will not give an answer until I don't do that myself. That's
okay.
the most.
Because one as a sort of phenomenological approach, one can imagine, right, that you have some in the code, right? It's looking at the local size of the gradients and adjusting the effective E over S. But I guess the first proof would be that somehow doing this, truncating at some low order using effective E over S would give you better agreement with the exact solution.
Let me see if yeah, I think that I delete that. Yeah, I delete that. I know what you mean, and I delete it. So,
okay. And one question on this slide. So in the E over S versus W, for the value 3.1, is it going negative at low W?
No. That's never negative. It's protected. It's always positive, because that is my initial condition, and I just push the W as small as possible, so it never goes to zero.
Okay, thank you.
Okay, so this was like what happens when it's an interpretation of this resummation. It's an interpretation, and it's a provocative thought that works. I will say, like, it works very well in this truncated system. But I want to go to the real beast, which was the other part, that the more general case, like what happens when you start to add more modes, and what happens with the asymptotic behavior of the distribution function. So since I sort of went a little bit step by step here, I'm going to rush a little bit. And when you do this, another expansion that emerges is that I didn't include any polynomials in the energy in the previous example that I gave, but you can generate those polynomials in the energy. And in this case, those polynomials in the energy, just for instance, capture how hard, in terms of the scale of momenta, which is weighted by the energy of the particle scaled over the temperature. So how hard it is, for instance, when particles that have large momenta, how the distribution function behaves, and whether or not there is some relevant aspects in this. And in this case, the generalization is a little bit bigger, because now you will have moments that depend on not only in the number associated to your Legendre polynomial, but also in the Laguerre. And those Laguerres, as I said, in the original approach of Grad, he said you can have those polynomials there, something that also the authors of DNMR theory did. And we did the same type of strategy. Like, we are not going to solve the total distribution function. We solve the moments, and the moments capture the sense of the time dependence. And notice that, of course, if I know the asymptotic values of the moments, I automatically can know what is the asymptotic value of the distribution function. And that is what, again, transeries is going to help me. And the type of dynamical system, if I do again, I rewrite the equations of the moments and so on, then I have a set of dynamical equations of motion, where this is n plus L dimensional vector. And the form of the equation is more or less like reasonable. It's those lambdas that appear here, those V that appear here are nothing else than matrices, as well as this gamma. And the interesting aspect is that you can use the same technique that I addressed before, but the difference is that you start to have that the series, the emergence of trans-series. Originally, I did it like, what happens when I have two, what happens when I have one, and then we did some numerics, and I was able at least to convince myself that those series emergent, and the full technique was developed by Ovidio Costin. Of course, it's a 60 pages mathematical paper, so there are some technical demonstrations there, which for my discussion are not necessarily important right now. But the interesting aspect is that, again, you will have some sort, yeah? Okay, I thought that somebody was asking something. But the interesting aspect is that, again, I have to resum a complete set of transmonomials, which are those zeta, which are those exponential terms weighted by some variable w. And I have, again, some asymptotic behavior, which is, again, determined by the size of the gradient, with some coefficient. And you can determine this just by, again, using the asymptotic ansatz, but in this case, for this n plus L dimensional system. So let me just briefly show what happens. We solve for, like, again, we had just very few moments. We did truncations just as an illustration. And we, again, compare what happens.
Can I ask you a question? Sorry. In this multi-parameter trans series, where are the Stokes lines? So before you had a Stokes line in the positive real axis, I imagine, no?
Everything is in the positive real axis.
No, but when you have multiple parameters, I would imagine that you'd have, you will have in different points. Is it also, all of these are associated to singularities in the positive real axis only?
Yes.
So you have multiple parameters associated to different exponentially small terms, all on the same axis.
Mm-hmm. They have to be, because they are solutions that are real, and you wrote a very nice paper of the reality conditions. It took me.
They could be complex conjugate as well, for example.
Yes,
so they don't have to be real.
It depends, explicitly speaking, it depends on the whether or not both the Lyapunov exponents as well as the power law anomalous dimensions terms. That we derive some conditions like when this happens, and yes, you're right. There are some terms that are complex or can be complex. We have some conditions about that. What happens when, for instance, the Lyapunov exponent is imaginary, or if it's real, but what happens also with the beta. So there are different conditions for that. And you have, in all the cases, to use the reality condition, because those moments are physical and they are integrals over the distribution function, which is defined in the real domain. So to answer the question, yes, that possibility is there for sure.
Thank you.
And just as a sake of illustration, we basically just select a very few of those moments. So we just solve a dynamical system with a different number of variables. And we proceed to do trans-series. It's more complicated. And here, the question that Ronald Janik asked, like, what happens with those sigma? How do you feed it? Here is where it starts to be problematic, because the moment that you do truncations, you know that your trans-series are not going to be perfect, but you can show that in some cases it will be relevant. And of course, you see that compared with the asymptotics, the resummation does a better agreement with the exact solutions numerically. But you start to see something really cool, which was that I always thought, and that was one of the biggest surprises of this work, that asymptotically, the slowest power law decay was coming from the pressure anisotropy. But there was a hidden term that was also decaying like 1/W. And when I analyzed where the origin of the 1/W was coming when we did the asymptotic analysis of the differential equation, and it was related with that. There is a very highly non-trivial coupling between any moment that you have here and the moment of the associated to the pressure anisotropy. And in that case, that particular moment survives entirely with only the moment C11, and it goes like 1/W. All the other moments drop out faster, like 1/W squared, like in this case that I'm showing here. And that was a hint that we were missing something in the usual grad expansion that you do for the distribution function at the level of how you truncate the distribution function. So we decided to pay attention to this, because there was a very provocative paper by Paul Romachke, who says that, okay, Hydro breaks down around PT or the order of 2 GB, and the description of the data, in this case, are those Fourier coefficients that enter into the particle multiplicities as a function of momenta. So the description of the data works pretty well and under very, very high accuracy for scales of momenta smaller than 2.5 GeV. But he says, oh, but if I am a little bit above or above in general, those are non-hydro transport, and those non-hydro modes dominate the spectrum in that regime. And of course, I am not saying that we can compare at this point with experiments, at least not me. But we did some sort of Gedanken experiment, which is that we can define some moments as a function of the energy and longitudinal momenta, and those moments measure different the hardness of the distribution function, as well as how anisotropic the distribution function is, and they are weighted by these n and m coefficients, and they are normalized over the equilibrium. Okay. And those moments can have some interpretation. For instance, for the particular case that we study, since we have that M20 is equal 1 because of the Landau matching condition, and the M10, for instance, is the normalized particle density. And we are going to focus mostly on what happened here. I'm not going to, because I know that in the method that I have, in the way that we have, you need to add too many transmonomials, and I don't care about that part, really. I'm just going to focus on the asymptotics. And when we did it, we start to realize, like, what are the dominant terms? And then we found out that there is a very cute classifications of what are the moments that dominate and determine the asymptotic behavior. And for moments that are very, very anisotropic, this M01, M02, M03, and M04, and so on, they are dominated mostly by this moment C01, which is the pressure anisotropy again. But we start to see that the moment that we start to increase the energy, the contribution that becomes dominant actually is this moment that was also decaying like 1 over W, this C11. And that is related with the hardening. So it means that the more energy, if I'm a little bit anisotropic, but I have a large energy, then I start to be sensitive to this particular moment. And we call this the semi-hard scale. And for the hardest modes, we observe that those terms are basically suppressed very fast, which kind of corroborates the idea that very fast particles, that fast the non-hydrodynamics modes decay too fast, and they are maybe insensitive. But there is this pretty scale, or this pretty window, where we can analyze what happens with the influence of this other mode that survives until the long time. And here we did some comparisons with numerics. Also, Mike Strickland did in another different ways the comparison. As I said, what I was interested was mostly in the comparison between those exact moments that you can calculate numerically with these asymptotics that comes from the solutions to the asymptotic solutions of the differential equations associated to those moments. And the first thing is that we observed, like, there is this slower thermalization when I have systems that are anisotropic and at the same time a little bit hard. And the thermalization of those systems starts to be sensitive to this other mode that previously was not appreciated. While if I start to be very anisotropic, but not so energetic, or this in the soft sector of the distribution function, it is more or less what we expect, that the pressure anisotropy is the mode that describes pretty well to higher order of accuracy the asymptotics of those modes. And this is really nice because it's also telling us that therefore the asymptotic behavior of the distribution function, at least when times are very large, is not only dominated by the soft physics, but also by the other hardening. And in this case, the slowest hard mode, which is associated to this C11, plays a fundamental role to describe. And here the numerics is overwhelming. And if I also evaluate what happens, for instance, at scales of energies, or the order of 2.5 GeV, which is where you expect from experiments that is not going to work. And keep in mind that this is just a toy model, and we study the time evolution. We see that the description, when I include the semi-hard mode, is better asymptotically, which when I include just the 1 over the first Ling order term. And it does much better job than if I try to include only one mode. And at the same time, this was to us properly, because then we can describe fully the physics of the attractor of the distribution function at very large times. And we can determine which are the modes that are contributing there. And as I said, the contribution comes not only from the pressure and isotropy, but for the slowest highly energetic mode, which in this case is this C11. So the hardening of the distribution function plays a role, and it remains to be interesting to understand this better, at what are the phenomenological consequences. And I know that I heard that there are some authors working on that. So I am really looking forward to see what they get. So the fact that I have a kind of different set of modes that contribute at late times for the distribution function, and that I can characterize the distribution function when I expand in those orthogonal polynomials, tells me that there is an idea that emerged from dynamical systems. Like, you have a lot of fast modes, which in this case are all those highly energetic particles, or modes associated with highly energetic particles. But there are also those modes that are like slow, that even in the long time survive. And this is related with the physics of what is the slow invariant manifold. So in other words, the fact that I can describe the distribution function by a very few modes asymptotically means that if I can hydrodynamize, or if my system hydrodynamize, is because I can describe it with only very few degrees of freedom. So I have a bunch of modes from my expansion, but then at the end, only the very few ones are able to do that. In this case, for the relaxation time approximation, one can show that, and we provide numerical, we tested numerically, that you need not only one mode, the pressure anisotropy, but only two. And this works, seems to be the tendency for the relaxation time approximation, not seems to be the tendency, is the tendency for the relaxation time approximation for the Bjorken flow. For the Fokker-Planck, which is something that we also did, it works, the concept. So just very few degrees of freedom contribute asymptotically. And there is a flow that I didn't talk about, but some people may have been familiarized, which is a flow that expands in some curved manifold, whose curvature at infinity is non-zero, and therefore the system is always in non-equilibrium. And that you can show that there is no slow invariant manifold for that particular system. We did it some time ago. And it makes us think about, like, okay, what are the conditions that you need for hydrodynamization then? The conditions are, you need to have a slow invariant manifold at least. So in other words, you need to have very few degrees of freedom, and if you don't have it, you will never hydrodynamize. That is kind of the condition that we got out of those, let's say, playing with those ideas and analyzing different cases. And let me just conclude this short presentation with what we know, at least in the conformal cases in kinetic theory, for Yang-Mills equations, for when I solve the full lane order collisional kernel, when I solve the Fokker-Planck, when I solve the RTA, and I compare with the asymptotic values at late times, which is first order hydro, and at very early times when I don't have interactions with free streaming. And there is a very universal behavior at both early and late time behavior. At early time behavior, everything is dominated by free streaming. At late time behavior, everything is hydrodynamic. There are also differences between those two limits. In the late time hydrodynamics, all the perturbations that the systems that have been studied so far show exponentially decay behavior, and at early time they have power law behavior. I didn't talk about that, but that is what we know so far. And well, just a little bit of conclusions, like we using the ideas of transasymptotic matching, we get renormalization of transport coefficients. Non-hydrodynamic transport is related with the role of a slow invariant manifold. And just also as a thought, like this is just the tip of the iceberg, hydrodynamization. And now we are entering into a regime where we have to start to understand not only analytically and numerically, but also at phenomenological level for people working in phenomenology, about the role of those non-hydrodynamic transport models. And some other type of questions that are like tentative, is like how to generalize to arbitrarily expanding geometry. What happens when you have phase transitions? And Shokamata did some recent work on that in resurgence. We don't know much about what happens in hydrodynamics. And some other thoughts is like what happens with effective actions and Lyapunov functionals, which we did something about that. I will not say that is complete, but we talk a little bit about how to construct Lyapunov functionals, which are like the partition functions somewhat for dynamical systems, and we did for the Webster flow. So those are kind of things that I wanted to address, and I thank you for the opportunity.
Thank you. Thank you so much for this presentation. Can I, is there some questions right away? I do have a question, but I should probably wait for.
So can I ask a question? I have to leave in like 5 minutes. It's just a semantic question, I think. So the Lyapunov exponents are defined, but basically they measure the how the closed initial conditions grow exponentially apart and form a chaotic system, right? So it's important for, you know, that Lyapunov exponents are actually positive. When you call these Lyapunov exponents and Lyapunov functionals and so on, are you just referring to just the exponent regardless it's because if it's positive, it sounds like it's the exact opposite limit of these attractors and so on, right? So any small change in initial conditions, you'll end up like somewhere entirely different. Yeah, so for Lyapunov, like traditionally defined Lyapunov exponents, SR would be negative, right? Mm-hmm. So it's just, is what you call Lyapunov exponent just sort of some exponential parameterization of the initial conditions?
Yes, but in this case, I'm solving asymptotically somewhere. So I agree that, and actually that's what I didn't talk about. Like when you do that in the other way around, when you expand in the UV or at the small w, then you will see precisely what you are saying, that actually is positive because everything is getting out from there. So I was just focusing in where I was located in the, and I was like very, very close when the solutions are basically merging towards the attractor. And of course, we have the minus sign there. So the usual, it's not the first time that somebody has pointed me out this. So I changed a little bit the signature sort of saying. And I just focus on how the perturbations, the distance between two initial conditions decay asymptotically.
Decay, yeah. So yours are decaying, whereas in,
yes.
You know.
Yes, exactly. But that is because I'm in the IR. If I am in the UV, it's something else. It's more like what you say. It's like growing.
All right. Yeah. Thanks.
Thank you.
Very nice talk, by the way. Thanks.
Thank you. I appreciate that.
So you're saying that if you could do the same analysis and you would also have exponentials, but with positive with a positive exponential there.
Actually, it's not the behavior, the asymptotic behavior is not exponential there. So in other words, when you analyze, and that is the analysis is more subtle actually, because one of the questions that somebody asks is how do you define the fixed point? When you are in the UV, the fixed point, you can have many fixed points and you have to analyze the behavior in each solution. And usually we were able to do that in this case by analyzing how the behavior is close to W going to 0. And what we find, what is surprising is to find that actually you have only power laws, you don't have exponential terms. And depending on the stability of the system, the power law can be positive, the exponent can be positive or negative.
The exponent?
Of the perturbation. The power law behavior. So you don't have exponents there.
So like the W to the beta kind of thing.
Exactly, it's W to the beta, but then you, depending on the UV fixed point where you are, you can have positive or negative. And in one case it's because one is the perturbation drops out very fast towards the pullback attractor. While in the other case it's not, because you are in a saddle, if I recall correctly right now.
But then you don't get asymptotic expansions.
You don't get it. No, those or any asymptotic expansion done in the UV has a finite radius of convergence. Okay. And you can do some analytical continuation to extrapolate that. and you actually get pretty nice results. We did it, and also other authors did it. But also what is impressive of that is that the radius of convergence is related with the asymptotic value of the transport coefficient eta over s for the relaxation for Fokker-Planck.
Then going back to what Goce just mentioned, then why would you say that you have a Lyapunov exponent in that case? Because there's no
no, because there are no exponents there. As I say, the perturbation is only power law. Sorry if I give the incorrect.
But in here, they're really not. They're actually exponentially decaying. So then they're
the IR, yes.
It's kind of the opposite, right? That very different initial behavior will go to the same solution after
hydrodynamized, yeah.
Right, so it's kind of the opposite.
It's the opposite. It's completely opposite, and it's something that as I say, I didn't talk about that, but I just briefly mentioned here. Sorry, here that this type of line that you see, the gray line, goes like W to some exponent. I don't remember the exponent. So it's kind of interesting that happens. And it's mostly because free streaming dominates there. So particles do not interact, they are flowing away. So and you have always this interplay between the exponentially decaying modes at late times and this expansion rate being dominant at early times. And that's why at early times, at least in Bjorken and Gupser, actually, you can also show that they are power law. And everything is again done by just analyzing asymptotically how the system behaves there. So that's the pretty usefulness that I found in this trans-series and transasymptotic approach, because you can get information to all of that. And I love it. I mean, I was very happy with that.
Other comments? I still have some technical questions, but I think that more comments before that maybe would be more useful. So, okay, well, people think I can ask.
Oh, sorry, maybe I have a quick question.
Yes.
All right, sorry for interrupting. So you were talking about rheology before with the shear viscosity. How much more complicated is this with, say, I mean, like the bulk viscosity, because that's always a difficult computation, and I don't know if it's really clear what that would look like.
That's a very good question, and you are asking me something that there is some work in progress, but it's much more complicated, because to give you a short answer without going into details, the equation of a state play a role in the asymptotics, and
right, I could imagine
the picture changes quite a lot. We will put this in a paper hopefully soon with Jacob Jankowski, Michal Spalinsky, and Sho Kamata about that, because we thought that it was going to be easy, and it ended up being absolutely outstanding. So I will let you know later on about that. There was, however, recently, like 2 weeks ago, an article where they analyzed what happens in the Hubble expansion. And the idea of renormalizing the bulk viscosity emerges there. However, it's highly symmetric system, and they use a very, if I recall correctly, simplified equation of a state, which allows them to do analytics, which is fine. It's just as a sake of illustration, and see how far it is. I feel that the real question is what somebody asked, like, how do you do this in a real numerical simulation? And that the problem, in my opinion, is open right now. Thank you.
Thanks. I look forward to your paper.
Please send me questions anytime.
Yeah, please interrupt anytime. But I wanted just to ask, in terms of the actual calculation of the transasymptotics, transasymptotic summation, how many terms did you calculate in both exponent, and did you include in both exponentials and 1/W? So of each one of the sums when you were comparing. So you were saying the different orders?
Yes, to the top of my head, I don't remember. We were playing with, this was like brute force, you know. So we were just like adding by hand certain number of terms in W, certain number of exponentials. For the first paper, if I recall correctly, we include 15 transmonomials for each order in the gradient size up to third order, if I recall correctly. But
Which transmonomials?
The exponential terms.
Ah, okay. Sorry.
But I just don't recall exactly. I mean, those numbers were like ad hoc somewhat because we were just seeing a proof of concept, like how it works and so on. I know that if you want to be accurate or be more precise about the radius of convergence and so on, you have to add a large number. However, it's surprising, and I would like to say this, that sometimes you don't need so much. And if you really just want to see the tendency of the solution, very few are enough to capture that. But you start to play also with this issue that, okay, I have a good agreement on 1 over W squared, let's say. But if I go to 1 over W to the cube and I start to play a role, then the curve actually can get worse. So after understanding a little bit better why this was happening, we understood that if you want to match exactly the solution, you have to resume over everybody. But computationally, that is very difficult numerically.
The coefficients that you calculated them basically numerically, the UKs, to what you called UK.
Yes, but they can be calculated by solving some. If you plug the answers in the equation of motion, you get some recursive relation that you can solve systematically. We explained how to do that, and then we just were able to crank it in a code. But as I said, the more of those terms you get, the more slow your computer wrote, and we were just like using as a proof of concept that at least you get a decent agreement, which is much better than the asymptotic expansion.
But in principle, if you have a differential equation, you could calculate, well, in principle, you could calculate the resummed expansion.
Yes, in principle, yes. We derived it, as I said, you have some sort of recursive relation in the coefficients.
The recursive equation will give you the coefficients, but
exactly.
The differential equation will give you the resummed series.
Yes, that is true. The difficulty lies more in the what I call the U sub k. Those are the difficult ones.
No, but you don't have to. That's why I'm trying to say that meaning Costin, for example, he didn't for his examples, he didn't. He calculated the resummed result. He didn't calculate it wasn't about calculating the coefficients. Would you be able to do it with this differential equation? I'm not saying meaning you might get the differential equation and not be able to solve it. So in the end, you have to calculate the coefficients anyways. Mm-hmm. But I'm just wondering.
The answer is in principle, yes, but it requires a lot of computational power, and we were not able to do that like in a more efficient manner. So we did brute force a lot, and we were able to at least improve a little bit the algorithm, but at the end we were just like, okay, we have to provide a good and reasonable description just to as an illustration of the method. That's the best of my answer. But yes, you're right. In principle, one can do it. You just pay a price a little bit with computational time.
Thank you. Any other comments, questions? So I don't want to keep on going, sorry. I just one more thing that, so did you manage to do some kind of matching between, meaning, are you able to use this to do some kind of matching between UV, IR kind of thing?
The answer is that, at least in the way that we did it, which is, and I have some sort of idea how to do that, but it's very hard numerically, again. which was a suggestion by, I forgot the name, somebody who has worked in resurgence for a while. So what we did was poor man's approach. As I say, you have the solution in the trans series and the multi-parameter trans series, and the best that you can do is just like fix the initial conditions, and we did a chi-square minimization for the sigma. So all the terms were determined accurately as much as we can, and then we just determine the sigma by using a chi-square minimization. In principle, you can do that by using other methods, but like complexifying the solution numerically and so on, but then and then you just match the amplitude of the oscillation with the amplitude that you have at from the trans series. But we were unable to do that really literally. It's numerically we failed sadly, and we spent 1 month on that, so you can imagine. So the answer is we did the poor man's approach. I feel that there should be room to do a better matching, and it would be really cool if somebody has some strategy that can provide me. I will appreciate any email or any information about it. But I was unable really, sadly. Like, as I said, we did the best poor man's approach by doing this chi-square minimization of the sigmas, and you get a reasonable description. It's not that you get something bad, like those plots, and the error bar is related precisely with the chi-square minimization. So that's why you see these blue bands.
Yes, sorry.
Yeah.
Thank you again.
Yeah, thanks for the question. It's a very relevant one, actually.
So yeah, maybe is it in the papers that how many terms you used for the?
I think that we quoted in the results section, in the comparison with the numerics. To the best of my knowledge, we did it. But we also mentioned the pitfalls that you have when you do this. Like we know that if you truncate, you have pay an error. And for instance, you see that here in one of the plots that it was like going very well, but then whoop, it goes away. So it means like your approximation is not reasonable, at least for that mode.
I have to say that, yeah, so I found that summing a few of them does work much better than you think, because you're not summing just the exponentials, you're summing the exponentials times that W.
Exactly.
And the W makes a huge difference, even numerically.
Yes, I agree with you. I was surprised that I was adding more and more, and my hope was getting better, and actually no. Only when I start to like going further and further and further away, I was like, oh, now I'm getting better again. But I didn't know how to have control over that, at least numerically. But we know that there is a pitfall there that you have. And actually, the less my lesson was like the less times you add, the better the agreement could be.
Yeah, so I have a comment about a little bit. So yeah, usually people using usual fitting to get this kind of sigma. But in principle, so as far as our expanded form is divergence fields, you have to go to the hyperasymptotics, right? So that's the main reason.
Mm-hmm. Right.
And also, if you expand around UV, so yeah, in that case, it's the radius of convergence is non-zero. So yeah, somewhat you can do some kind of analytic continuation from 0 to infinity, but this infinity, W equal infinity is really the dangerous point. So you cannot arrive at W equal infinity.
Mm-hmm.
So yeah, that's another reason, roughly speaking.
Yes.
So any other questions, comments? You can always, hopefully, if you have any other questions that come from here as well, just you can write them down and we can try and also address them in the open question session. So yeah, please do write them down, and we can just try and discuss them if you think of any other questions in between on Friday.
Yep. You can also drop me an email if there are questions, or to my good friend Sho Kamata. So it'll be great.
So but if there's no more questions or comments, perhaps we first stop recording. So thank you so much, Mauricio, for the nice talk and for the discussion and everything. So, and thanks everyone for all the questions also in between. So